Visual food recognition has a wide application for many food-related services. Recent work has achieved significant progress in food recognition, such as individual health monitoring, dietary and intake management, and arguably the most popular social functionality, food recommendation and social networking. However, it is difficult to obtain enough data for some food dish types. Therefore, training using conventional approach becomes unreliable. Some recent works start to explore the task using feature learning. Existing approaches on food recognition, including some feature approaches, usually formulate it as a multitask classification task, where the recognition is attempted along with other attribute recognition, such as GPS location, ingredients, cooking recipe. However, such information may not be always available, and the collection of them requires considerable extra efforts and costs. Different from existing works, we built a fusion framework that unifies the conventional many-shot and feature learning from food recognition. Major features of proposed method are listed here. It can classify both many-shot and feature classes with a unified classifier. We improve the classification performance by leveraging on different modalities of both image representation from a feature extractors and textual embeddings from a language model. We have also explored the rich interclass correlation between different classes via a graph neural network to further enhance the robustness of the final class representation. With the following slides, we show the overall architectures of our framework. It consists of 3 modules. The first is the module of fusion of many-shot and feature learning. It will be used to train a CNN using the many-shot food images and then extract the classification weight, which is the class-specific vector that is used to classify different classes. The trained feature extractor will be used to generate a prototypical vector for feature food classes, which is class representation based on average of feature class image features. The second module runs concurrently with the first module, called Generation of Class Label Embeddings. This module tries to use available class label of food and generate semantic embeddings using context-sensitive BERT model, which does not require any additional attributes. A new semantic loss between these 2 modules is introduced for the purpose of measuring similarities between image features and its respective semantic embeddings during training. At the last step, both the combined classification weights and semantic embeddings will be used as input. A graph convolutional network is used to map the dependency between different food classes in terms of image and textual representation. After training of GCN, the output class representation can be used to build the final classifier. To be more specific, we denote the GCN structure as G with inside node as V and H as E per layer. We define node value as the classification weights we obtained from the first module, and H strength Qij is defined as output after softmax operation of the cosine similarity between nodes. Please note that during the computing of H strength, the semantic embeddings is also used together with classification weight to calculate the cosine similarity. Further, denote Hi as layer L as the representation for node I as the layer. It is updated based on the following equations. The detail aggregate function is defined as in the third equation, which uses a FC network to perform nonlinear combination of node representation. The final output of F is weighted based on the respective H strengths between nodes. Regarding the combine function, we adopt a concatenation solution used in jumping knowledge networks to provide additional direct connections between representations from all previous layers to the final output, by which the model can learn to selectively exploit information from all intermediate layers. We evaluate a framework over different food benchmarks. 2 datasets mentioned in the paper are UEC Food 256 and Food 101. Please refer to the papers for details about the experiments. From the tables, we can see our method can yield consistent improvements against fireworks for all 5-way classification scenarios. To sum up, we propose a fusion learning framework for visual food recognition. It is a unified system that can classify both many-shot and feature classes at the same time. It uses both image features and text embeddings in generating food representation. Interclass dependency between food classes has also been explored to enhance robustness of the class representation using a GCN. We will continue to work in the direction, and we believe that the current framework can also be extended to other application domains, such as similar few-shot or fine-grained classification tasks. Thank you.